Before writing code, let's look at our final hardware setup. We are interfacing a 5-volt active buzzer directly with an AT89C51 microcontroller. Our goal is to create an automated notification system. By the end of this build, the microcontroller will trigger an audible beep, turning the buzzer on and off in precise 500 millisecond intervals. To replicate this circuit, you need the AT89C51 chip, an active buzzer, breadboard, jumper wires, capacitors, and a 5-volt power supply. You also need an 11.0592 MHz crystal oscillator. This acts as the system's heartbeat, providing the exact clock speed for accurate delay functions. Securing this exact component list ensures that the timing logic we compile in our software will perfectly match the physical limits of the hardware on the bench. Let's map out the AT89C51 wiring. To control devices, we use a digital output pin. Use port 2, pin 0, at pin 21, and route it to the buzzer's positive terminal. Watch your polarity. Active buzzers are directional. Reverse terminals will not sound. To complete the circuit loop, run a wire from the buzzer's negative terminal to ground. With that physical path connected, the microcontroller now has a clear route to push electrical current to the audio device. To understand how we control that current, this graphic breaks down how digital logic translates into action. When the software sends a logic 1 to P2.0, the chip outputs 5 volts, and the buzzer emits a continuous tone. Dropping that pin to a logic 0 cuts the voltage, and the device goes silent. Alternating continuously between high and low creates a repeating square wave pattern, producing an intermittent beep. Our programming task is to write instructions that toggle these two binary states over a strict timeline to create our desired audio rhythm. Here is the complete embedded C source code required to execute that repeating pattern. Step 1 maps the hardware to the software. We use the S-bit keyword to declare that port 2 pin 0 will now be referred to in the code as buzzer. Next, we need a way to pause program execution. We create a custom delay_ms function that uses nested for loops. Forcing the processor to count through these loops stalls the execution for a set duration. The limit on that inner loop, counting up to 112, is precisely calculated to stall exactly 1 millisecond when driven by the 11.0592 MHz crystal we installed on the board. Finally, we enter an infinite while loop. We set the buzzer to 1 to activate it, call our delay function for 500 milliseconds, set the buzzer to 0 to silence it, and wait another 500 milliseconds before repeating. Compiling these instructions and flashing them to the chip locks that high-low logic into a permanent automated task. Let's power the board and check the real-world execution. You can verify the system is processing by checking the status indicators. The Run LED is lit, and the elapsed time clock confirms our main loop is active. Look at the timing diagram. The physical sound output perfectly tracks the digital waveform, hitting a strict 500 millisecond cadence. This basic mechanism is exactly how digital output pins manage warning alarms, microwave timers, and notification systems across consumer electronics. We started by establishing our hardware layout, routed a specific output pin to an active buzzer, and then translated binary high-low logic into a timed C program. Now, try altering the delay values to build your own custom alerts. That is the core of digital output control.